Swayam Prabha. Digital India. Educated India.
We learned about bipolar junction transistor, high frequency model, and also that of MOSFET transistor. Now we will start building circuits using these transistors again, and we will calculate the frequency response of individual stage. If you remember, a few lectures ago we did common emitter, common source or common gate, and emitter follower or source follower circuits. So we will redo those circuits again, and we will add the capacitances due to transistors in this particular analysis, and then we will calculate what will be the pole locations or zero locations. Again, we will keep the analysis simple so that we will latch on to right insights rather than mathematical details all the way. After looking at frequency response of an individual transistor like a bipolar transistor or a MOSFET transistor, in this lecture we will be looking at high frequency response of different stages that we have already looked at. For example, the first one we are going to look at is a common emitter or a common source stage. So let's draw the schematics first. So on the left side we are seeing a common emitter amplifier. On the right side I have drawn a common source amplifier. Going forward, we will be always comparing bipolar and MOS transistor stages together so we can draw parallels between the two configurations. The Rn is representing the previous stage output resistance, and I'm not showing the bias voltage which is part of Vn, or to make sure that the transistor Q1 is in forward active region or transistor M1 which is in the saturation region. Now in this particular case, the schematics that I have drawn, it does not show any capacitances. What we will do now is based on what we learned for bipolar or MOSFET transistors high frequency model, we will start inserting the capacitance values. So for BJT case, we have C mu, which is going from base to collector. We have C pi, which is going from base to emitter, and CCS is from collector to the substrate. We are also going to show a load capacitance CL over here. Similarly, for MOSFET stage, we have CGD, which is gate to drain capacitance, which is an overlap capacitance when the MOSFET is in saturation. CGS for saturated MOSFET, and we have CDB, drain to bulk capacitance, and then we have CL, which is the load capacitance or the capacitance representing loading from the next stage. So let's try to analyze both circuits together one at a time and then draw parallels from it. So the small signal circuit for the common emitter stage, I would recommend you draw it on your own first and then insert the capacitances in the picture. So in this case, we are assuming that Rout is much greater than RL, and hence we are ignoring it. Now we will add the capacitances for the bipolar in this picture. You can draw a similar circuit for MOSFET stage, and you will find the only difference will be R pi will be infinite for a MOSFET stage. So we can draw a unified model for both BJT and MOSFET amplifier, an equivalent model, and then analyze that. So here is the unified model for both BJT and MOSFET. So you can compare this to the previous bipolar model, and you can say that, by the way, this VTH and RTH is a Thevenin equivalent looking back at this particular node. Okay, it should be fairly clear once we go through the little bit of analysis. So BJT, for BJT case, we say that VTH Thevenin equivalent looking back is V in R pi divided by R pi plus R in, because we have two resistors here, R in and R pi. So the voltage V pi is given by resistive divider effect between R in and R pi, and that's what our VTH is, Thevenin equivalent. And RTH is going to be R in parallel R pi. CXY is the capacitance between node X and node Y, and our job is to split that gap CXY so that we have two capacitances which will go from node X to ground and node Y to ground. And once we do that, then we know how to figure out the frequency response of this circuit. From node X to node Y, we know that there is gain in both cases, either bipolar or MOSFET case. The gain is given by gain from X to Y is equal to minus GM times RL. We will apply the Miller principle, and what that will do is it will remove this capacitance CXY, and then that capacitance will be added over here. So this capacitance is added from node X to ground, and that is CX over here, and the CY we're going to call it over here CY. So we know that using Miller principle, CX is equal to 1 plus GMRL times CXY. We know that GMRL is the gain, and this is a large number, so this will be approximately GMRL times CXY, and CY is equal to 1 plus 1 divided by GMRL times CXY. So this will be approximately equal to CXY because GMRL is large. If this is something that looks like new to you, then please look at the Miller effect and how we split the gap between node X and Y, which is whenever we have a gain from node X to node Y and we have a capacitance between those 2 points, then we can move that capacitor from node X to ground and node Y to ground using Miller effect. And that's what this is all about. Now we can do comparison between common emitter stage and common source stage, and then we will have a unified response for both these cases, common emitter stage and common source stage. So the Thevenin equivalent VTH in case of common emitter is V in times R pi divided by R pi plus R in. In case of common source stage, VTH, the terminology might be confusing here, apologize for that, but this is the Thevenin, let's call it VTHE, and that would be equivalent to V in. Since gate to source resistance is infinite, that's what we get. RTH is equal to R in parallel R pi, and CX, which is the capacitance going from node X to ground, which will be approximately C mu times GMRL. Again, these are for the BJT case. CY will be equal to C mu, C in is equal to C pi, and C out is equal to CCS plus CL. And we'll do something similar for MOSFET case, where RTH, Thevenin equivalent input resistance, will still be equal to Rn, Cx will be equal to CGD. This is due to the Miller effect. GMRL, Cy is equal to CGD, small number. Cin is equal to CGS, and Cout is equal to C drain to bulk plus CL. What we are trying to do is we are trying to use a common circuit for both BJT as well as MOSFET amplifier so that we don't have to do the analysis again and again. And this kind of draws out the similarities between the two circuits. So node X, there are only two nodes in the circuit, node X and node Y. And you are seeing a resistance and a capacitance to ground from those nodes. So then using this, we can quickly figure out the poles. There will be two poles. Pole at the input will be input, which is node X. That will be omega P input is equal to reciprocal of RTH. So you can see here, this is the only resistance that you will see from node X to ground, and you will see the total capacitance, this one. And that should give us omega P in, which will be in this case C in plus GMRL CXY. We will also have another pole. If we look at the circuit, we will have a pole at the output also. And the resistance at output is going to be RL, and we will have equivalent capacitance due to this. You may wonder, why am I ignoring this GMVX transconductance? When we are computing frequency response, what we are doing is we are removing all the independent voltage sources, we are connecting them to ground. So if VTH goes to 0, then automatically this GMVX will also go to 0. So we will have only this part of the circuit which will come up with a frequency. So pole at output, which is at node Y, omega P out, that is given by 1 divided by RL and C out plus CXY. I have done a numerical example in my notes. Please go through that carefully. So I have given you numbers for a common emitter stage, and you can walk through the example by yourself as a practice problem. As I told you earlier, using Miller effect, what we do is any kind of, if you have a gain A and any kind of capacitance from like X and Y across gain A, we convert that to capacitance going to ground from each node. I also showed you that when we have a capacitance connected from one node to another node with a gain, then that also can give rise to a zero. And that is not being predicted using Miller effect. So I showed you a technique which will give you a zero frequency. So let's do that in this particular example again. So this is our generic model. Now if we observe the highlighted portion, which is the CXY, that shows a capacitance CXY connected across inverting stage. And what we did and what we talked about in the previous lecture was it gives us a 0. Let's figure out the value of this right of plane 0. And the thought process was as simple as this. So we have a capacitance CXY, and here is Vx and here is V out or Vy. So at zero frequency, literally what's going on is this V out is going to be 0 at zero frequency. Let's say that zero frequency is S of Z. So at frequency S of Z, V out is equal to 0. We are not physically connecting V out to 0. It's just that the transfer function will happen in such a way that V out will be equal to 0 at the zero frequency. So what that means is these two components will not carry any current at zero frequency. And we can have current which is flowing this way and that will flow that way. So at zero frequency, V out is equal to 0. So V in times SZ CXY, that would be the current flowing through the capacitance CXY, and that will be equal to GM times Vx. As I already said, there is no current flowing through C out and RL because V out is equal to 0. Correction here, this should be Vx. So we can say that S of Z will be equal to Gm divided by Cxy. Since this is positive, it's a right of plane 0, and you can already see it's a real 0. We figured out two pole locations and we figured out the 0 location, right of plane 0 location. Then our transfer function is going to be V out divided by V in is equal to AV, that would be your DC gain, 1 minus S divided by omega Z, sign minus because it's a right of plane 0, and then we'll have 1 plus S divided by omega P input, 1 plus S divided by omega P output. Input and output, those are the two nodes for our common emitter or common source stage. Now let's do an example of high frequency response for a common base or common gate stage. High frequency response of CB, common base or common gate stage. I will draw the two schematics and we will follow the same train of thought. Initially we will draw the schematic without the transistor capacitances, and then we will add the transistor capacitances and we will do a common frequency response equation. We will find out what are the two pole locations. And here is a common gate stage. Now we will add the capacitance, the transistor model capacitances for both sides. C pi, then we have C mu, then we have CCS, and we have CL, which is across the RL. So there is a slight difference in case of a MOSFET stage. From source of the MOSFET, we have a capacitance which is CSB, source to bulk. Then we have CGS, CGD. Here is C drain to bulk, CL. So V bias is AC ground. So 2 points I wanted to make here. One of them is, in this particular configuration, our input is at the emitter or source and output is at the drain or collector. So there is no capacitance from input to output in this configuration, as a result of which we don't have a Miller effect. So we will draw some of the concepts we have already done. One of them is, what is the resistance at node X? So node X is going to look like 1 over GM node. So it's we are assuming that R out is infinity for first cut analysis. So Rx will be equal to 1 over Gm. In that case, the input pole will be omega P input will be equal to 1 divided by Rin parallel with 1 over Gm of the transistor, along with capacitance at node X. And capacitance at node X is going to be Cx is equal to C pi or CSB plus CGS. So this is for MOSFET case and this is for BJT case. Omega P out, the pole at the output location, output node, is going to be, what is the resistance at the output node? In this case, it's going to be RL in parallel with all the capacitances which are at the from output node to ground. So let's write that out. So that would be RL times CY. So in case of a BJT, CY will be equal to C mu plus CL plus CCS. In case of MOSFET, this will be equal to CGD plus CDB plus CL. So one comment here is, if you look at this particular factor right here, omega P in, that looks like, if you say that the GM dominates, 1 over GM is dominating in the parallel combination, which means the resistance looking into the emitter or source is a lot smaller due to high GM, then omega p in will be GM over Cx. And in this case, Cx will be C pi or CSB plus CGS. So we can say that the input pole location, this location, is fairly close to Ft of the transistor, which we have seen omega p in is close to Ft of transistor, which is Gm divided by C. So this is a very high frequency, since we are talking about Ft of the transistor, which could be hundreds of gigahertz. So in the overall frequency response, it's the output pole which will dominate the response. Again, I have done a numerical example as a practice for you. You can look at the notes, and fairly substitution based example, but it gives you an appreciation for numbers for a common gate stage. Now let's do high frequency response of the third configuration we learned, which is follower, emitter follower or source follower. Let's draw a schematic for both. Initially without transistor capacitances, and then just insert the capacitances which matter. Now we will add the capacitances, C mu. Now in this case, we will not add the CCS. I would like you to think about why I am not adding it. The reason is already one end of the capacitance, CCS, is connected to ground over here, and the other end is connected to VCC. So it will, when we do the AC analysis, this CCS capacitance will be grounded, both sides will be grounded. So it will not participate in the evaluation of the transistor. So this is the key point you have to remember when you are doing the analysis. Every time you don't have to put all the caps that you know in the transistor for analysis. So this is where you can prune out the ones which don't matter and only keep the ones which matter, so that your analysis becomes a lot simpler. C pi, and we have CL at the output. Similarly for MOS, here we have CGD, CGS, and then we have capacitance for CSB plus CL. In this particular case, we ignore the capacitance CDB because it's connected from VDD to ground. And IB is for DC biasing of the follower. So small signal equivalent circuit for emitter follower is going to look like this. Now we can add the capacitances, C mu, and we have C pi over here, and then we have CL going from V out to ground. In this particular case, I would like you to stop the video and do the analysis by yourself using KCL and KVL, and then we'll compare the notes. It's important to go through a little bit of grunt work by yourself. Specifically, I would like you to practice when we have capacitors and resistors together, so that you can go between G mode versus resistance mode, which I have taught you for ease of analysis. So go ahead and do the practice, do the KCL, KVL, and our goal is to figure out what is V out over Vin. Please try to do this by yourself, and then you can look at my solution, which will show up on your screen in a fast forward manner. So this looks like a complicated analysis, but that's okay. We have a quadratic equation in the denominator, so we can use that to figure out the two poles of this particular equation. Interesting point here is the numerator. What is the numerator telling you? The numerator is telling you that there is a left half plane 0. When we say left half plane, what that means is it's a negative number. And when we say right half plane, for example, if you look at the sigma and omega, j omega here, So left half plane will be 0 at this location and right half plane will be 0 at this location. So this would be positive number and this would be a negative number. So in this particular case, we have a left half plane 0 with omega z, mod of omega z is given by gm over c pi. So this is all brute force KCL KVL analysis that we have done. And now I will show you the trick that I have taught you earlier. Using that, you can also figure out the same location of the 0. So if you remember, we have capacitance going from input to output. So this is our V input and the capacitance value is C pi, and at that value we have plus minus V pi, and then we have this output V out where we have a current which is flowing in like this, Gm times V pi, and there is some R and C connected, some Z connected from V out to ground. So at the 0 location, what we are saying is the current is flowing this way and V out goes to 0 at 0 location, 0 frequency. So we say that V in is equal to V in times S of Z and C pi is equal to, we rewrite this again, V in minus V out S of Z C pi is equal to minus Gm times V pi. We already know V in minus V out is V pi. So V pi S of Z C pi is equal to minus Gm V pi. So S of Z will be equal to, remove the V pi, minus Gm C pi. So we say that we have a left half plane LHP 0 since it's negative. You can do the exact same analysis for source follower. Some of the values will change, but pretty much you will see something very similar. In case of source follower, what you will see is the left half plane 0 will be minus Gm over CGS. And again, that goes close to the FT of the transistor, so it's very far out there. You can refer to notes for the detailed analysis of the source follower. Again, it's algebra that you just have to go through it, convince yourself for once, and then kind of take the insights with you. Now we will move into frequency response of a differential pair. So let's draw the differential pair schematics. As we discussed earlier, to analyze differential pair, we partition the circuit in two parts. One is for differential input and then for common mode input. So for differential input, what we do is we say that the tail node is a virtual ground node, and then we only do analysis for the half circuit. So let's draw the half circuit for each one of them. Including effect of the caps. It's going to look like this: CL, C mu and C pi. For the MOSFET case, it will be CGD, CGS, CDB and CL. So it's the same analysis that we did earlier, which gave us the equation was V out divided by V in is equal to AV 1 minus S divided by omega Z divided by 1 plus S divided by omega P input and 1 plus S divided by omega P output. AV is the DC gain and 1 minus S divided by omega Z represents right half plane 0. So one thing to note here in this configuration is C mu or CGD, these two capacitors, They are generally small numbers. However, we try to get as much gain out of this stage, and they get multiplied by the gain from input to output. They can dominate the frequency response. So I'll repeat the point. The CMU and CGD, even though they are small numbers to begin with, because we have large gain from input to output over here, due to Miller effect, they will get multiplied by the gain from input to output, and they can deteriorate the performance of your amplifier. So how do we improve that situation? One of the solutions is to use cascode transistor to reduce the Miller effect, and let me explain that to you. So let's draw a gain stage with cascode transistor. So main transistor is M1, and this is our MC cascode, which has a DC bias VB. We will also add the CGD. Let's label the node. This is gate and this is drain. If you look at this particular example, due to cascode device MC, the gain from gate to drain, gain gate G to drain of M1 is given by minus GM1 divided by, what's the resistance looking up and down? Resistance looking up, if you ignore the output resistance of MC, it's going to look like 1 over GMC. So that would look like GMC. C is denoting the cascode. Now the two GMs, if they are in the same, about the same size, then they will be in the same ballpark, and that would look like -1. So equivalent Miller capacitance is at gate, that will be now equal to CGD times 1 plus gain. The sign plus because we know that the gain is negative from gate to drain. So this will look like CGD 1 plus GM1 divided by GMC. So that will be approximately equal to 2 times CGD. So CGD is quite small. CGS is very large, but CGD is quite small because it represents overlap capacitance. And you can see earlier we had the whole gain of GMR out of the transistor, which was multiplying CGD, and CGD can be 10 to 50, so it could be a large number. In this particular case, it's just 2 CGD, so it's not that bad. So we can say that cascode stage will reduce the Miller effect impact without really reducing the gain. So before we stop, I will draw a schematic of a cascoded diff pair so that you can understand how this works. The gain from the input to the intermediate node is only -1, because looking up we see something like a GM node, and looking down we have R out of M1, so GMC will dominate, as a result of which we have gain of -1. So this is the cascoded differential pair where you can eliminate Miller effect using cascode transistors.